at the moment that I start to sharing on YouTube, it's going to be recorded on YouTube, but I didn't start recording here yet.
E aí, Giovanni, tá dando?
Tá tudo certo.
O povo tá conseguindo entrar?
A Filomena tá ainda em dúvida, se você puder ajudar aí pelo... E a Silvia entrou no Colóquio errado, ela entrou no 7. É que o sistema do ímpar não é amigável mesmo. Ó,
Não.
Silvia... Hi, Silvia.
Hi.
Hi.
Ciao Silvia.
Ciao Filomena.
Ma non riesco...
Hi Liliane, Giovanni.
Scusate, ma non sono molto brava con queste cose. Non riesco a capire come... Ma non c'è una...
Ma
io sono in...
funziona, né?
Sì, but I have entered because I clicked on the... They said enter, but I do not have the ID of the meeting and the password. So I don't know if I'm able to do everything I should do.
Hello, Monica.
Hi, everyone.
Hi, Monica.
Nice to see you. Hi.
Hi, Monica.
Ah, Tanaka, are you sleeping?
Kazunaga, are you? Thank you, Kazunaga. Okay, this is a real sacrifice because it's night in Tokyo.
No problem.
Monica, how are you, Monica?
Well, I'm surviving, Filomena.
But still, you are still in lockdown?
Yes. Yes.
Oh my God.
Well, I mean, not really. I mean, we can go out and things are open and everything. The university is not. So this means we have to lecture online.
University is not open yet. My God.
No.
My God, that's terrible.
That's terrible, yes.
Still either. We are teaching online, still online, Filomena.
My God.
Yes. And we will be teaching online also next semester. So, well, I thought, Katsunaga, you would be in the Olympics right now, watching the Olympic Games.
Yeah, on TV.
On TV.
On TV.
Yeah, how to say, it's a very strange Olympic game. And no audience.
Yes, I know.
No audience, yes.
Yes. And also, I mean, the guys that are competing are not allowed to go outside the Olympic villa, no?
Yes.
They are not.
Yes.
They are not allowed to visit the city or to visit other places in Japan. They have to.
Yeah,
to
just
stay
they
in
can
their
stay hotel and the stadium.
Yes.
But some guy, went out secretly to the town.
So he escaped.
Yeah, anyway, it's a very crazy situation in Tokyo now.
Yes. I can't believe that. Yes, it is a complicated thing to have the Olympic Games precisely in the pandemic. No, this is very complicated.
Yeah, it's crazy.
Crazy. Yes, I think so too. But I guess the athletes wanted to compete. They really wanted to go.
Yeah, exactly. That is the fact that they already had to wait 1 year, and for people in a sport and.
Yes, 1 year is a lot. No, they cannot wait another 3 years or whatever. No.
Yeah, it's for me it's unbelievable. Without audiences, they play very good way.
Yes.
So they train Yeah, so
Yes, it's not, I guess it must be very strange for the athletes not to have anyone there, you know, to cheer them up and so on. Yeah.
They seem happy, I mean, when they win anyway.
When they win.
There are, if they win, of course. There are some, you know, the press is there, I think, and with the organizers. I don't know. I was against them, but now that I watch from time to time and I see that, I mean, you know, they train the whole year, and actually many years to do
That's
this.
right.
And so
Right.
it's very frustrating. Assume that you have to give a talk and you have been prepared for years, and then they say you cannot give the talk.
One more
That's
year.
impossible. I wouldn't prepare a talk for years. I mean, maybe
Not
one
years,
month.
months and months and months, and then they tell you no, you cannot give the talk.
This is going to happen to you, Filomena, today.
Okay. For me, doesn't matter.
Be
It's not a
prepared.
great loss. I finished to prepare my talk an hour ago, so I didn't spend much time.
Okay.
I have a question for Katsunaga. Katsunaga, in your university, I see Blackboard during the night. Are you?
no, it's a fake. It's just a photo.
I thought.
I'm worried.
No, he doesn't.
Yeah.
Let's say the truth. He's in bed, I think. He's in his bedroom,
So
and as soon as he ends his talk, he will go to sleep.
Okay. Very worried.
Are you wearing a shirt, Katsunaga, or is this just a photo and you are in your pajamas?
In fact, he is not really Katsunaga. He's somebody giving a speech.
Over the pajamas.
So the first speaker is Katsunaga, right?
yes,
Yeah.
Right.
Yeah.
Fortunately for him, no?
You in Italy are almost on vacation, Filomena. In Italy, you're almost on vacation.
Yes. I will leave at the end of the week. Go to some island on the sea.
It's a good day.
Nice.
But you are on vacation, Liliani, no?
No,
We
had a break. We had a break
restrictions,
some time
so
ago.
essentially, no, it's not a good atmosphere in Tokyo now.
But in Brazil is a vacation time, no? July.
No.
Huh?
Right now we are teaching because our semester is like out of schedule and we had started some semester. But even when we had vacations, I didn't travel, Filomena. I was at home.
This I know. This I know.
I'm
mean,
really
vacation
afraid
just,
of going out.
Yeah, vacation just means not to go to the university. Not to go, not to teach.
Yeah. Time to work other things, not teaching, but
to work.
Hola, Manuel.
Daniel,
Hola.
can
Hola,
we
¿qué tal?
start
¿Cómo estamos?
our section?
Hey, Manuel. Hi.
Hi, how are you?
Hi. Yeah, it's fine.
¿Cómo me va?
It's not. It's not so easy to explain in this moment. Yeah, I have my mother in the hospital for situation.
What happened to her?
Because he had a surgery, angioplastic surgery yesterday. Yeah, I'm totally crazy in this moment. Yeah.
So he had a plastic surgery, yeah?
Yeah. No,
Hi, Thomas.
Delicate.
Hello.
Hi, Thomas.
Oh, hi, Thomas.
Hey, you guys.
Hi.
Nice to see you all.
Yeah.
Yeah,
Not so nice. I mean, it would be
Not
nice.
so
yeah, other way would be nicer, of course, yes.
Kasunaga, what time is for you? Is it for you?
It's 7:30 in the evening.
Oh, yes, Thomas, but Kasunaga, but Tanaka?
How to say, just opposite. So time difference is just 12 hours. So midnight to 2:30.
2:30.
Yeah.
2:30.
Not so good.
Wow. So that's late.
Yeah, it's okay.
Okay,
Giovanni, I think it's time we should start.
Okay, we can begin.
okay. Let's start. So, good afternoon, everyone. First of all, I would like to thank Professor Kasunaga Tanaka, Liliane Maia, Manuel Delpinho, Filomena Pacella, Thomas Bartz, Elisa Fili, Angela Pistoia, and Susana Terracini for their availability to give this talk to us at the Brazilian Matemática Colóquio. The Brazilian Matemática Colóquio is the most comprehensive scientific gathering of the Brazilian mathematics community held in biannually since 1957. It's counted the participation of undergraduate and graduate students from all over the country, as well as great Brazilian foreign research of great international renown. I'd like to strongly thank Professor Monica Klepp and Silva Tingolani for their help. Without them, it would be impossible this section to happen. I would like to thank everyone, people who is watching us on YouTube. Now, you call Professor Marcos Duor, representative of the scientific community, to welcome the participants. Please, João.
Okay, good afternoon, everyone. I just want to say a few words. I'd like to welcome and thank everyone for participating in this event. Through the internet, we currently have the opportunity to watch lectures by leading research from many parts of the world, and this can be seen as a positive point of the current scenario that we are living today. In particular, today, in this afternoon, we will have the pleasure to be able to watch the research lectures from Professor Tanaka, Professor Maia, Professor Delpino, and Professor Pacella. Also, I would like to take the opportunity to inform you that we also have today, in this week, in this colloquium edition, another section of partial differential equations and application. Each will take place on Wednesday and Friday at the same schedule as this one in the afternoon. So I thank you for everybody, and I give you again the words for you, Giovanni.
Thank you, João. Now, let's call the first speaker. The Professor Kasunaga Tanaka is a full professor at the Waseda University, and he will talk about the formation argument under PCP condition in the application. Please, Professor Tanaka, the word is yours.
Thank you for introduction. First of all, I would like to thank organizers for invitation and for giving me a chance to give a talk here. It's really my honor. Okay, let me start my talk. Today, I would like to talk about the formation argument for essentially for scalar field equation. It's a rather old topic, but recently I find some new trick, and so I would like to talk about new trick. And my talk is based on joint works with Professor Silvia Singolani, Marco Giaro, and also with my colleague Jun Hirata and Norihisa Ikoma. Okay, let me start. And okay. In this talk, I would like to introduce a new deformation argument, which works in a rather in a special situation, and also sees a group action, and the new type of palette-smell condition plays an important role. And how to say, my work is largely motivated with the work by Bresticky and Lyons, and also it has other applications. And first, I would like to put a focus on nonlinear scalar field equations. The equation is like, how to say, I think almost all people here know that, this equation very well. And anyway, how to say, here I would like to introduce you conditions on GU. This is proposed by Bresticky and Lyons, essentially. Anyway, we assume space dimension is greater than or equal to 2, and we how to say, assume the following 4 conditions. One is how to say, G is a continuous function, and second one is how to say, essentially it has a subcritical growth. And also G2 is about behavior near 0, and it's a negative, it has a negative gradient. And also, how to say, this is a kind of global condition, and so the picture of G is something like this picture. And these conditions are very, I think, loved condition, and it's called almost, how to say, necessary and sufficient condition. And under these conditions, Bresticky and Lyons, and this is for space dimension n greater or equals to 3, and Bresticky, Giaro, and Cabian, it is for n equal to 2. They show the existence of positive solution firstly, and later, and the second paper, they show existence of infinitely many possibly sign-changing solutions in for this problem, and they seek for radially symmetric solutions. And the approach is how to say, they consider a constraint problem, and essentially they try to minimize Dirichlet integral and the constraint. So how to say, integrand of cap GU is equal 1 for space dimension greater or 3, or for 2 equals 0. And this is a natural constraint from positive identity. And they show how to say, this, say, it has a minimizer, and it's a positive solution. It's has to lead to positive solution after suitable scaling like this. Okay. Anyway, I think this theorem is very general, and when I started, how to say, study of PDE, how to say, I like this theorem very much, and it covers 2 types of nonlinearities like this. This is for something like nonlinear Schrödinger equation, and this is something like Allen-Cohen equation. Anyway, how to say, when I saw this Bresticky and Lyons theorem, I wondered how to say, is it possible or not to show this with a mountain path theorem? Okay, and anyway, natural functional corresponding to this problem is this functional. And my question is a probably stupid one, and anyway, I try to show the existence of a solution using mountain path argument. And this works, how to say, in bounded domain very well, but for in Rn, even if we we assume radial symmetry, it's not so easy. anyway, how to say, easy, how to say, point is it's very easy to see you have a mountain path structure. Mountain path structure, I mean, at there, this is 0, and there are small mountain around it, and somewhere outside the mountain, there is a negative place. And so, anyway, it's very easy to see a mountain path structure, but the difficulty is, how to say, to check parallel condition for this functional. And anyway, I was not a good student. I tried and I failed. So reason is as follows. Okay, so anyway, if we, how to say, take a parallel sequence, it means, how to say, I of uj tends to b as j tends to infinity, and we also assume I prime uj goes to 0 in the sense of dual normal H1. This is a definition of H1 norm. But under the condition of Bereziki and Lyons, since there is almost no relation between cap z, this is the integrand of the small g, and also there is no, how to say, utilization. So probably this is not enough to show boundaries of uj or also strong convergence of uj. So in general, it's difficult to show parallel condition. Okay, so anyway, so I try to find a new trick to deal with this situation. Okay, so anyway, there is some fact corresponding to Bereziki-Lyons theorem. I found it with Jiang in 2002, and we show the following things. And anyway, we find Bereziki-Lyons and or Bereziki-Garo-Cabian solution enjoy mountain path characterization. That means let U0 be your solution even by their constraint minimization. I mean, how to say, they use constraint minimization, and we need you to use a suitable scaling to get a solution. Anyways, such a solution can be characterized by mountain path. It means energy level of either U is a B, and B is defined by minimax value. This is just a mountain path value, and this family is a family of continuous paths joining 0, and somewhere functional is negative, probably outside of a small ball. Okay, so anyway, it's rather difficult to show existence of solution by mountain path theorem, but we can show mountain path characterization. So I thought it's nice if we can find a way to get a solution by mountain path directly. Anyway, this scalar field, nonlinear scalar field equation is a typical problem with scaling, and it gives a, how to say, a very good institute to other problems. So if we know other way to approach this problem, maybe we can get, how to say, we can solve some other problem. So I tried. Okay. Okay, so aim of this talk is to give a positive answer to the question using a special deformation argument under new type of parallel condition. Okay, and I also show existence of infinitely many solutions. And before I show you my trick, I will give a comment to preceding and related works. I will tell you later, and it's very related to our deformation argument, is how to say, generation of PSP sequence. About the definition of PSP sequence, I will give later. And anyway, we generated a kind of special PS and parallel sequence at mountain path level, and also some minimax levels. This fact is firstly used, how to say, by Jiang in his paper for normalized solutions. But how to say, I would like to say, when he wrote this paper, how to say, we shared office and in Scuola Normale in Pisa, and I think I helped him very much. And also later, 10 years later, I wrote, how to say, with Hirata and Ikoma about how to say, such a trial for nonlinear scalar field equation. It's a typical problem, and we show how to say through a mountain pass. In some sense, we succeed to get a solution, but for infinitely many solutions, my technique is very complicated, and this it's not so clear, and it's not so difficult, but it's not so direct. And also there are many approaches to use the mountain pass theorem. One is, I think, to use a so-called Struve-Montusi trick. So firstly, we part of the function a little bit, adding something like L2 norm, and for almost all, how to say, small perturbation, we can find bounded Paris-Mare sequence, and for part of the equation, we can find a solution. And after getting some a priori good superior estimate, we can pass to the limit, and we can also, in some sense, get a solution through the mountain pass using Struve-Montusi trick. But how to say, I think I like this method very much, but we need to part out the equation a little bit. So I'd like to find a more direct method. And also recently, many people use a positive manifold or natural constraint to get a solution. I think this is also a good idea. And finally, here is three papers. One is with Hirata and myself, and Ikoma and myself, and Professor Singrani and myself, in which, how to say, we developed a deformation argument in augmented spaces, and this gives, how to say, in some sense, a direct proof of existence of solution through mountain pass theorem. Okay, so mainly today I would like to concentrate about this paper. This is for nonlinear scalar field equations. Okay, so I would like to talk about the differential argument for under PSP condition, and I would like to set up the problem rather abstract setting, and we consider, how to say, Hilbert space with physical action, and we consider functional C1 function, which is defined on Hilbert space. Of course, we can generalize this situation a little bit. We can also deal with Banach space and or Banach manifold. Anyway, other conditions are rather, how to say, special. I would like to introduce you. First assumption is just, how to say, there is a C0 group action. This is a usual C0 group action. And the second condition is a rather tricky one. Okay, so anyway, we have to say, consider product space, R product E, and we write it M. And we regard M as a Hilbert manifold. And we introduce metric by this formula. And we assume this metric is of class C2. I think this is very tricky condition. Since we assume this action is just, how to say, this is physical action. So we assume this map is just continuous. But, okay, so here we request this matrix is of class C2. And so this is a rather tricky situation, but later I will give you an example. And also, I would like to introduce a functional with this formula. This is a functional defined on this product space. And I define, so theta is a real number and u in E. And so this is a, in some sense, scale. And we consider, how to say, functional with two variables. Okay, so since we assumed, how to say, this action is just C0, usually this is just, this should be continuous, but here we assume this function is of C1 on the manifold. Okay, and so these two assumptions are very tricky assumptions, but this works to understand, for example, nonlinear scalar field equation. And under this assumption, we introduce a positive functional PU by, in this way, PU is, so since this is C1, we differentiate with theta and we plug in this. And so this is a kind of a PU equals 0 is a positive identity, and I would like to call this functional positive functional. And now I would like to introduce PSP condition. Okay, so let it be the real number, and I would like to introduce you a PSPB condition. This is a condition like this. Assume UJ satisfies these three conditions. First condition and second condition says just these are parallel sequence. But here I would like to add PJ, so positive function goes to 0. And I would like to assume, so if UJ satisfies these three conditions, UJ has a strongly convergent subsequence indeed. And I also call UJ as a PSP big sequence if UJ satisfies these three conditions. So it's just how to say a parallel sequence with this additional condition. And I would like to introduce a notation KB. This is a critical set, but here I have to say require PU equals 0. So this is a smaller set than usual critical set. And also I would like to introduce a notation like this. This is a level set notation. This is okay. So this is not how to say standard, but I think you can understand quickly. Okay, and our deformation theorem is as follows. Okay, so assume how to say this tricky condition about the group action, and we assume PSP holds. Then we can see KB is compact in K. So this is a critical set also requesting a positive identity. And for any neighborhood O of KB, and for any epsilon bar, there exists a epsilon and continuous map. This is a deformation flow. Such that first condition is so I think these are standard, and so maybe I don't need to explain precisely. So anyway, when T equals 0, this is the identity, and for lower level, this is constant. And also, this is all always decreasing, and also so except a neighborhood of critical set, this decreases. Also, this set is mapped to this set, and if KB is empty, so it means that there is no critical point to satisfying positive identity. This level set is mapped to, this should be plus. Okay, so, and also, if K is even functional, this gives a, how to say, flow is also is a odd. So we can use different deformation instead of usual deformation to show existence of critical point. Okay, so since our assumption of phi is a tricky one, I will to give an example. It's for nonlinear scalar field equation. Okay. Okay, so we set is a radially symmetric H1 function, and also we use Caesar group action phi theta with this formula. So this is just a scaling, so with E theta. And we can, of course, we consider this function, which is corresponding to nonlinear scalar field equation. And so about the tricky condition, I would like to write a norm. So since the definition of norm is something like this, so here this is a phi theta H1. So we can compute using rescaling in this way. And also we can compute this guy in this way. So we can easily compute this one in this way. So with this formula, you can see this norm is of class maybe C infinity, and also this functional is of class about C1. So this functional is setting satisfies our assumption. And about positive functional. Just how to say, this is a derivative of this with respect to theta, and we plug in theta equals 0. So we have PU like this. If we set equals 0, this is just a positive functional, positive identity. Okay. Okay, so, and also, as I said before, it's rather difficult to check Paris-Mero condition, but for PSP, it's very easy to check. Anyway, so if UJ is a PSP sequence, it satisfies these conditions. This is first two is just a Paris-Mero condition, and the third one is a good how to say, positive identity, positive function equal to 0. Since we combine this guy number formula 4 and formula 6, we can get a boundedness of gradient U in the this integration of cap G Uj. Okay, so there, and of course we need some computation, but it's not so difficult, and we can say Uj is bounded, and also we can extract a strongly convergent subsequence in this radially symmetric sobre space. So now Verst-Guillon's theorem is easily deduced from our deformation theorem. So also we can get the existence of infinite many solutions via symmetric mountain path theorem. Okay, so sorry, in the remaining time, I would like to give you how to prove the deformation theorem. It's a little bit tricky, but I think the idea is nice. Idea is natural. Okay. So anyway, idea is to use this, how to say, functional J, and we consider in the product space this one. So original functional space is E, but we add one dimension, and we consider in product space. And we consider the formation in this product space. And anyway, we have the following properties from the definition of J theta U. Anyway, J theta is just a rescaling of I in some sense. So it's a very good relation with I. Anyway, IJU is like this. And also, since this is a group action, we have this. And also, if we differentiate it with theta, we have this, we use here, and this. Okay, so anyway, important thing is that if we differentiate with respect to theta, we get a positive functional. And also, if we differentiate with respect to IU, we have, anyway, we have something like this, and just since the theta is a group action, we have this. In particular, writing D equals d theta and du, we can write d du theta is just like this. So about differentiation with respect to theta, we have a positive functional, and differentiation with respect to u, we have a original I prime. Anyway, so with theta, this is shifted in this way. Since we, how to say, introduce a metric with this formula, we can see differentiation with respect to j at theta u is just like this. So this is just a differentiation of the original functional and also positive functional. Okay. And now we set, so since we consider the formation argument in product space, we also introduce a critical set in product space. So this is a KB children is how to say, just a critical set at level B for J. Here, how to say, there is no condition related to positive. It's included in differentiation with respect to theta here. And we also consider level set like this. Okay. Anyway, please note that if theta u belongs to KB children, this is nothing but K theta u belongs to KV, original critical set with positive identity. And also KB children is empty if and only if KB is empty. Anyway, with this relation, we can easily see the following relation. Okay, anyway, we assume condition phi in the PSPB. Then firstly, if we assume KJ, is a Paris-Smith sequence for augment functional J, then we have, from here and here, we can see since this goes to 0, this means that positive functional goes to 0 for shift is different, and also I prime go to 0. So this means phi j uj is a PSP sequence. And so by the condition PSPB, this has a strongly convergent subsequence. In particular, KB equals 0. It is not empty. So limit of this must belongs to critical set. And conversely, if critical set is empty, then this KB tilde is also empty. So then there exists a delta 0 such that for small delta 0, if J is between B minus delta 0 and B plus delta 0, this is how to say, in some sense, gradient is has a positive lower bound. Okay. Okay. So for the sake of simplicity, I would like to consider the case KB called empty set, and we would like to make a proof of the formation theorem. So first step is we construct a deformation flow for J in product space. Okay, so since we assume KB equals 0, we would like to find something like this. And such a deformation is very easy to obtain using an ordinary differential equation in product space like this. Here, this is a pseudo gradient vector field, and also associated to this functional, and this phi is a suitable cutoff function. Okay, and so anyway, for theta u, which value of j is close to b, this is how to say, we have this lower bound. So we know the direction to which functional j decreases. So using how to say standard argument, and we can find such a deformation for j in product space. Okay, so now, okay, so anyway, so in some sense, we project and we obtain a flow. Anyway, first we obtain a flow in product space. Along this, j decreases, and also since there is a projection, so using a group action, and if we take how to say some kind of projection like this, so this is a so using this how to say relationship, then we can get a desired flow, and we can give a proof of the formation member. Okay, so I will give some corollary and remarks. And anyway, the first corollary is if we have this function phi and PSPB, and anyway, if KB is 0, then this for epsilon small, this set is deformable to for lower level structure. Anyway, I think this corollary is rather interesting. Anyway, in this, how to say, corollary, KB is not a critical set. It's a critical set with positive identity. And here I consider just an only scalar field equation. So any solution satisfies a positive identity. So this is not so interesting. But if we consider fractional equations, in some situation, it's very difficult to check positive identity. But how to say, this corollary says critical point without positive identity does not contribute to topology of level set. So I think for all solution obtained through minimax theorem satisfies positive identity. And probably it's difficult to find a solution without positive identity. And also corollary 4 is to say, so about the generation of PSP sequence. Anyway, if this tricky condition holds, and if B comes from some minimax method, then since there should be a topological change between B plus epsilon and B minus epsilon. So if PSPB holds, there should be a critical point at level PB. But if this does not hold, we can find a PSPB sequence. So, okay, so this is how to say what we did about 10 years ago. Okay. Anyway, so under this PSP condition, the formation works. Sorry, it's time. So anyway, I how to say planned to give another application. One is a nonlinear shortcut equation. In the same way, but computation and estimates are more complicated, but we can use this idea. And I plan to introduce you my joint work with Singrani, and I'm very sorry, there is misspell. Yarrow and myself, and also for normalized solutions. And also there are another, how to say, application about nonlinear application in 3 private domains, something like this. So in this case, group action is say something like this, and with this action we can also use a information argument. I would like to stop here, and thank you very much.
Thank you very much, Professor Tanaka. Now, do you have any question to Professor Tanaka? We start with Zoom's people. Any
Maybe
question?
I have a question. Can I ask a question?
Sure, please.
No question, Daniel.
Okay, so this, what can you say under your general conditions about the set P of U equals to 0? Because in applications that I know of, this is kind of radially homeomorphic to the sphere in the space, but maybe you consider a much more general situation. And then the question is, can you kind of constrain the functional to the set P of U equals to 0?
I think it's a good question, and but anyway, I think it's related to natural constraint, and usually, how to say, when we use a natural constraint, regularity of a manifold is important, I think, and sometimes we need to, how to say, struggle with regularity of Bose manifold. But here, how to say, in some sense, I avoid manifold, and so if anyway, if we are far away from manifold, there is a deformation to decrease the functional. So in some sense, I'm sorry, I escaped from that question. I'm sorry.
More question? Daniel, do we any question from YouTube?
No, sir, just some people saying that it was a good presentation. Thank you so much for your presentation.
Okay, thank you, Professor Tanaka, for this very, very nice talk. Okay, thank you.
I'm very sorry. I mistake the time, and it should be 35 minutes. I'm sorry, I talked
no
almost
problem.
14 minutes. I'm very sorry.
No problem. Thank you. Now, let's call the next speaker, Professora Liliane Maia from UNB, Brasileiro University, and she talks about let me see here, positive bound state to nonlinear shortcut equation via the Harry method. Please, Liliane, the word is yours.
Good afternoon, everybody. Thanks, Giovanni, Silvia, and Monica for this kind invitation. It's an honor to be here and to show some of these recent works, and it's a pleasure. So I'm going to talk about some recent results with Benedetta Pelacci and Delia Schiera from Italy. And basically or particularly today on the real world case, let's say, of Shocard equation. So the general Shocard equation is minus Laplacian of u plus, and today we're going to show some results with a variable potential v of x u, and this non-local term with a convolution I alpha with respect to u to the p and u to the p minus 1. We're basically interested in positive solutions. And I'm going to give an overview of the Shocard equation because I don't know about the audience, how much people are acquainted to the Shocard equation. And then I'm going to talk particularly on the case we treated with p equals to 2, for example. Okay, so the general Shocard equation would be for n bigger or equal to 2 alpha between 0 and n. The convolution is realized with this Reed's potential, a alpha modulus of x to the n minus alpha. And then we treat the case where p is in this range. So the first comment I want to give is why p on this range. But before that, I'm motivated by some physical problems too. So the case we treated is with a variable potential v. And let's see how far we can go. V is going to be a positive potential, but can oscillate, can come from above, can come from below. The physics behind this equation when alpha is equal to 2, p is equal to 2, goes back to Froelich and Pecars with a model of Polaron, which is some real world problem in condensed matter physics. And I always try to learn a little bit from where the problems come from. So this is our free electrons in a ionic lattice, which interact with photons associated to deformations of the lattice. So basically the V of X that we see comes from this deformation of the lattice where photons and electrons are interacting. This was first introduced by Shocard in '76, modeling one component plasma. Lieb also worked from a real world problem, Lieb and Thomas, studying ground state energy of strong coupling polarons, and many others. Anyways, I don't know much of the physics, but I tried to learn a little bit to get motivated on the equations. The physical model is really when p and alpha are equal to 2. The Shocard equation is related to several other partial differential equations with non-local interactions. For example, when studying standing wave solutions of Hartree equation, this is the equation that comes up, and when the term of the convolution is with this sign, we say it's a Shocard focusing nonlinearity. The autonomous Shocard equation that comes from that one have been studied for many years, but mostly recently, many people are touching this and trying to get more and more information on the Shocard equations. So I cited some, but there are many others that have recent nice results on this. An interesting paper that I refer is a guide to Shocard equation by Moritz van Schaftingen, where they give an overview of the state of the art of the problem up to 2017. So for those who want to know about Shocard equation, don't know much, this is a great review paper on everything that has been done up to recently. Okay, what about this convolution potential that comes into play, and what's the role it plays? Okay, in order to have the variational formulation of this problem, the integral that is going to come up have to be defined. And it's defined depending on hardy little Sobolev inequality, which is this inequality written in red. And depending on where your f is, you are going to have the integral well defined. So this gives the constraint on the p that we have, because for us, the f is going to be u to the p. And then, because of Hardy-Littlewood-Sobolev inequality, you have to have this integral term of the convolution I alpha convoluted to up times up. This has to be it's bounded by Hardy-Sobolev inequality, and it has to be bounded by some integral that is finite. So it gives you the range where you have to work in order to have this well defined. Because of f plugging in f equals to u to the p, we end up having that if you take u in H1, it's continuously embedded by Sobolev, continuous embedding in this Q space. And this happens even only if P is in this range. So we end up with a range where we can work Shocard equation variationally. In this case of my presentation today, I'm going to stick to the physical problem where P is equal to alpha and equals to 2. If you plug in this information, you end up with the dimensions between 2 and 6. So for my particular case, I'm going to be restricted to these dimensions. But there are other restrictions imposed by what I want to do that is going to give n between 2 and 5. But up to now, just from Hardy-Littlewood's inequality, I would be able to work between 2 and 6 dimensions. Since this is the dimension that I'm able to work, I can treat the critical points of the functional associated to the equation. So that's the action functional associated to Shocard's equation in this range where P gives the convolution term well defined. But now, going back to some works where the V is variable. So the first works go back to Pierre-Louis Lyon in '84 when he treated a potential V of x below some limit V infinity. So in order to get critical points for the functional associated functional, it was possible because when V is below V infinity, you can apply concentration compactness. And this was one of the examples that Lyons gave in order to apply concentration compactness and get convergence of PS sequences and solutions for the variable potential problem. But it's the classical potential that comes from below. What can we say about potentials that come from above or which oscillate going to some limit V infinity? So that's the challenge. Go beyond and see, since we cannot apply directly concentration compactness, what can we do in order to get on the same spirit the solutions for the critical points for the function? Okay, when V of x approaches V infinity from above or oscillating, then higher level energy levels have to be searched. This requires a deep study of possible lack of compactness of the bounded PS sequence due to unboundedness of the domain in Rn. So this is known, it's understood by most of people in this audience. And then we have to search for bound states at higher levels in versions of the splitting lemma introduced by Struve when trying to understand what is going to happen to a Pallas-Mail sequence if it does not converge. This immediately furnishes compactness at quantized energy intervals where the so-called problem at infinity plays a role. So the so-called problem at infinity, in this case, since V approaches infinity, is going to be this autonomous problem, non-local term, and the V infinity constant here. This has been studied. A review of all the results about this are in this work of Moroz van Schaftingen, where they gather all the information, gave more information about the positive ground state solution. Okay, the autonomous problem and uniqueness of positive solutions. Because we are trying to see if we find solutions for a potential which is coming from above, and we are trying to avoid some symmetry, we are going to need some uniqueness information. This is classical when you try to approach Schrödinger equations, for example. This happens here again. Existence of positive solutions to this autonomous problem goes back to Lieb and Jans, and these results have been extended by Moroz and van Schaftingen, the autonomous case. The autonomous problem has a positive radially symmetric least action solution in C2 for any P in that range that I talked about Hardy-Littlewood inequality, Sobolev inequality. So existence is no problem, it's positive, it's radial. But what about uniqueness? Uniqueness property is known up to now for P equals to 2, alpha equals to 2, and dimensions 3, 4, and 5. So it's still a big open problem. Find uniqueness of the autonomous shortcut equation for higher dimensions and for other P's, not 2 and alpha not 2. But since the physical problem is P2 alpha 2, we decided to face the physical problem and see if we can get other results. But still, the uniqueness is a big challenge in studying shortcut equation. So what we got was the existence result when V is a variable potential. For alpha equals to 2 and P equals to 2 and N 3, 4, or 5, because then we have uniqueness of the ground state solution of the autonomous problem. And V under some hypotheses that I'm going to list and to present now, we also have positive solutions for the variable shortcut equation. So what are the conditions in these potentials that we were able to present in order to regain some positive solution? Okay, in order to go to this infinity limit, it has to decay with some power term times exponential decay, and you can have in our approach either some exponential decay greater or faster than 2 square root of infinity, or if you have an exponential decay of type 2 square root of infinity, which is related to the decay of the ground state solution, then you have to have some constraint, which I'm not going to detail now, it's just some constraints in the power term. But this is basically optimal in terms of the decay you can have as V goes to infinity. So it can come from above, from below, oscillating, but it has to have some special decay in order to regain a solution. These are optimal decays, and let's see what we had to do in order to get this solution. Okay, a review on this type of results, okay, when the potential is variable, is the result of Klebb and Salazar 2013, they got existence of positive and sign changing solutions, assuming some symmetry on the potential. This is a result of Monica with Dora, which is very important when studying variable potentials. Then there were results of Cingolani, Clapp, and Secchi, 2012, where they also used symmetries to obtain solutions for the Shocard, in this case with a magnetic nonlinear term. What happens if you assume symmetry? If you assume symmetry on the potential V, then you have the properties of the potential. This is going to give critical points in the function with symmetry. Then you minimize the functional on a symmetric Nehari manifold. So, assuming symmetry, you can do this in this scenario of symmetric functions, and then recover some compactness. Symmetry increases the least action level, allowing to construct Palais-Mail sequence, which is also a minimizing one, but in higher levels on a problem constrained to Nehari symmetric. So that's an idea of what we found, what is interesting in these works. So you have a symmetric minimizing level, which lies in a range where compactness properties hold. The idea is to, as they do there, good candidates are found where suitable translations of the ground state solution in points that are far away from each other, preserving the symmetry of the problem. So you sum this kind of bumps, and then when they are far away, you can estimate the interaction between them, and then you can lower the level of energy in order to find or to be with a PS sequence in the range where Palais-Mail symmetric holds. The idea is pretty much this. The functional decay property of omega, which is the ground state positive solution of the autonomous problem, is required. Nonlinear Schrödinger equations, for nonlinear Schrödinger equations, for example, exponential decay plays a crucial role. In the case of autonomous Shocard, it depends on P. When P is greater or equal to 2, and that's the range of P's where Clapp Salazar worked, and there they get the exponential type decay, existence results with symmetry solutions are obtained. When P is less than 2, one sees that real non-locality feature of autonomous Shocard, as the non-linearity in this case is not focusing enough. And then the decay of omega is not exponential, but plays a polynomial type interaction. But in the presentation today, I'm going to talk just about P equals to 2. So this is for another chapter of results. So we crucially depends on how the ground state decays. So I review here the results of Moroz-van Schaftingen for P equals to 2. They have that if let W be a least action solution of the autonomous problem, then for alpha between n minus 4 integer part and n minus 1, it results the least action solution decays with this power of x decay and this exponential decay. If alpha is equals to n minus 1, then the ground state solution decays with this power of polynomial decay and this exponential decay. So that's where our estimates are going to be very tight. We use not only the exponential decay, but we also got some information or stick to the polynomial decay in order to get the best decays for the, let's say, the variable potential. And as usual, as most of you know, when trying to find critical points, we can restrict ourselves to the Nehari manifold, find the infimum on the Nehari, and this is going to give a critical point for the action functional, therefore a solution for the Shokard equation. So this is the classical setup. Twice differentiability holds when p is greater or equal to 2, and then the Nehari manifold is fine, is C1, but it does not hold when p is less than 2, so you have to be a little more careful. In this case, we are talking today, p is equal to 2, so we are fine, the Nehari manifold is smooth enough. And then, associated to the problem, there is the problem at infinity, which is basically the same problem, but v is not variable, v is v infinity, a constant. You have the infimum here, and all happens. Okay, what are the challenges or the difficulties when facing this problem? Looking for a positive solution when v is variable, we have naturally requires a comparison with p infinity. For instance, v approaches from below, which is Pierre-Louis Lyon, or from above is one kind of approach. The approach we are doing is not from above, not from below, it's oscillating, for example, so we need some uniqueness results in order to get some range where PS condition holds. And this is possible only for these constants, as I talked in the beginning, for the physical problem in dimension 3, 4, and 5. Show PS sequence lies in the action level where some compactness property hold, perform with this uniqueness, we can show this, perform a careful comparison between the asymptotic decay of the solution and the asymptotic decay of the potential. This is very well known for Schrödinger equation, and then we did developed some for the non-local term and how it behaves. As we do in these cases, the big thing is to find candidates, since we are not going to have a ground state as in the autonomous problem, try to find candidates in order to get a PS sequence and then find the limit. The threshold is given by the interaction of two copies of the ground state translated very far away. This is a copy of the ground state translated to RZI, and here you have the interaction of these terms. But this time, when we are in the Schrödinger equation, this is just a local term. Here it's a non-local term, and then you have to evaluate how they interact, even spreading out with this non-local term here. But anyways, we were able to get that this interaction is basically of this size. It's the exponential to the 2 square root of infinity times potential term r to the minus n minus 1 over 2 when alpha is less than n minus 1. And it's of this value exponential times potential, power of r, if alpha is n minus 1. So this is going to guide everything that we have to do, because all the terms have to be compared with this threshold in order to see in which level we are in when taking a Palais-Mail sequence. Okay. Crucial estimate is then to see what is the role played by the potential. And then we were able to work in our problem for n in these ranges that we are working with in the following sense. If this continues, tends to the infinity, with this kind of decay, where sigma is in these four possibilities of the theorem that I didn't repeat here, but it's those four possibilities, exponential very fast or exponential of the same type of epsilon r, and then you have a term here that can compensate. Then we are able to prove that the interaction of the potential term with copies of the ground state translated far away is of small order. So this is crucial because then you are able, with this estimate, you are able to estimate the energy of these bumps, two bumps that we created, and see that this term does not define the sign of, or the difference of the energy level and the energy level at infinity. So this is going to be a small order term, which compared to epsilon r is not going to play an important role, let's say. And what about the nonlinearity? This time we have a nonlinearity which is, has a convolution term. So at some point we have to see how the copies of two bumps are affecting the convolution term. Even if they are far, far away from each other, what happens about this convolution? Does it help the interaction to change in some sense? So we're able to evaluate this interaction and see that basically what you are seeing here in the convolution of this sum is there is a piece which is important on the first bump. There is a second piece which is important in the second bump, and then there is this epsilon r term. Basically, the difference is this small or epsilon r term plus small order epsilon r terms. So this difference is going to play an important role at the end to see how the energy is going up or down depending on this interaction. Finally, what do we do? The whole idea, as most people know now, because it has become very standard when trying to find this kind of solutions, is take a convex combination of these two bumps put very far, far away from the origin. Project them on the Nehari manifold. In order to project them, since we are using just powers, it's a homogeneous problem in some sense, although it's not really homogeneous because of the convolution. You get, this is the t that multiplied by the u function or the key function here, this convex combination. This is the t that projects the function on Nehari. And then we prove that if we are working with this key two bumps, the t's are bounded uniformly as r goes to infinity. So this is important at the very end estimates. And these are this is the core of solving a problem on these paths. The idea is project this convex combination of two bumps in the Nehari. Look at the energy and see if it's below two copies of the energy of the autonomous problem, the ground state level of the autonomous problem. If this is below, then you are going to be in a range where Palais-Mail works fine. More than this, you have to see if one bump is below some the infinity level, which is the ground state level of the autonomous problem, plus something very small. So we have these two estimates. This is a core estimate. I'm not going to go into the details here, but that's when you see how the V potential can be, what decay, best decays it can be in order to still have some subtraction of the two copies of the energy in order to be in a range where Palais male holds, okay? So I'm not going to give the details, but it's where we used very much the interaction between the potential and the copies of the ground state far away from the origin. And then you introduce also classical argument, a barycenter function, and then you calculate the barycenter of functions in this action level below C infinity plus alpha. And then we are able to prove that below this level and projected on the Nehari, the barycenter is different from Z1, which is the center of the ball that we are putting in the beginning, the combination of two bonds. So this is the end of the proof. What do we do in this case after all these estimates? You start with a ball centered in Z1 with the radius 2 from, and then you have the boundary of this disk. For each y, which is a combination, a convex combination of these 2 points, of course, you create a function key or u of lambda r with a bump at RZ1 and a bump at RZ2. So you have a convex combination of 2 copies of the ground state solution. Project these 2 copies, okay, summed copies, on the Nehari manifold. If the R is far, far away, and if the V potential has that kind of decay, even if it comes oscillating to the infinity, we are able to prove that the energy is below 2C infinity. It's like 2C infinity minus something. So you know where these copies are ending up. They are ending below this energy. Suppose there is no critical point below this energy. So you can deform on the Nehari set and end up with a function with these 2 copies projected on Nehari deformed in a level C infinity plus alpha. But at this level, we're able to prove that the barycenter minus Z1 or is different from Z1, or this difference is not 0. So take this point in Rn and divide it by the modulus. Since you can divide because this is not 0, you are getting a point in Rn on the boundary of the ball. So if you compose all this, it's a continuous function which retracts this disk on the boundary of this disk. And this is impossible by Brouwer fixed point theorem. So you cannot have a continuous retract. What happened then is that when you did this deformation, it was not possible. So there is a critical point, and then you find a critical point for a problem like this in this level. All the estimates are not shown, but are crucial in order to get all these compositions. And I thank you for your attention.
Thank you, Liliane, for this very, very nice talk. Now, do you have any question to Liliane? I start with Zoom's people. Do you have any question? No? Marco
I think that Marco has a question.
has a question. Okay, please.
So, it's Daniel again, sorry. Michael went to chat and he said his microphone is not working. So I'm just gonna read what he wrote, right?
Okay.
So he said, hi, thank you for the talk. And my question is there some particular reason why it appears N1 in the choice of alpha when estimating Epsilon of R, or it is just a matter of computation?
The way I presented the N-1,
Yes.
the N-1 here is because we go and do some abstract result and then apply it to the case where we know uniqueness. So I put it here and didn't explain well, but this N-1 is just a matter of proving a thing which is more general for any N, but then at the very end, you have to stick to the cases where you know uniqueness, and then you go back to N 2, 3, 4, and 5. I don't know if I answered your question.
Okay, thank you, Marco. More
He said,
question?
thank you so much.
More question? No?
I have a small question, Liliane. I believe that uniqueness, you only need uniqueness in the non-symmetric case, but in the symmetric case, uniqueness doesn't play a role.
Doesn't play a role,
right?
Right. Here we didn't want to assume symmetry in the V, so we had to pay the price of uniqueness.
Right. Thank you.
Thank you. More question to Liliane? No? Daniel, do we have any question to YouTube, to Liliane from YouTube?
No, sir, just some people say, like Gustavo say, very nice talk. Thank you so much, Professor Lilian. And Olympio Miyakaki say, congratulations. Thank you so much.
Thanks, everybody.
Thank you, friends. Thank you, Liliane, for this very, very nice talk, as I said. And now I would like to call Monica Clapp, because Monica Clapp is chairwoman right now. Monica is here?
Yes, I'm here. I am very slow with the computer, so, okay, but I have unmuted already. Thank you, Giovanni.
The Zoom is yours.
I think we have about 5 minutes, or should we go on?
Maybe let's get a break, a small break, okay?
Okay, let's take a 5-minute break.
Okay.
So everybody can go and get some coffee or whatever. And we start at 2. Well, no, at 2 in Mexico, at 4 in Brazil or whatever, in 5 minutes.
Mônica, maybe you can ask for Manuel Delpino share his screen. Okay?
Yes, share and unmute.
Yeah, okay.
I almost forget to unmute. Thank you.
Si te queremos escuchar.
A ver, espérate, déjame correrme para acá, que la luz está un poco rara.
Sí, estás muy rojo.
Faz muito tempo que eu não escutava em espanhol. Good. Muito bem.
Sí, por supuesto.
Sigues estando rojo, pero menos.
Ok.
Sí, bueno, lo cierto que en la cocina, the kitchen is the only place.
Doesn't matter, Manuel. Te vamos a ver muy chiquitito.
Anyway, I have to see if the screen works. Yeah.
Right.
Just a second.
Okay,
Okay, perfect.
works.
Can you see it? Full screen?
Yeah.
Okay. So I will come back to my original position.
Ready?
Yes. Yes,
Okay.
I am.
Okay. So it is my great pleasure to introduce our next speaker, Manuel Del Pino from University of Bath, and he will be speaking about dynamics of concentrated vorticities in 2D and 3D Euler flows.
Okay, thank you very much, Monica. Thank you very much, the organizers, for the opportunity to be here. So it's very nice to be in this conference and also to see many friends, which is maybe not so often. Very happy to see you here. Okay, I will speak today about a problem that is not quite a problem in calculus of variations. However, the spirit of the type of things we do with it is a lot of what we have been doing for many years with semi-linear elliptic equations, and particularly in singularly perturbed problems. So let me introduce you the Euler system, the Euler equations, in 2 or 3 dimensions. So n will never go beyond 2, but beyond 3. And, well, that's complicated enough in this equation. So this is an evolution problem, which is a transport equation for the velocity of an incompressible fluid, okay, which in ideal circumstances and under no viscosity present satisfies this equation. So this is a system. Actually, you have the gradient of the pressure, and this pressure is a sort of Lagrange multiplier that comes out of the incompressibility condition, okay, which makes this a system. U can be a vector of either 2 or 3 components, and I will consider first the case of 2 dimensions. So in reality, this formula is the same for 2 or 3D. If the velocity field is called U1, U2, functions of a space variable, which now I assume has 2, then the omega, the vorticity of the solution U, of the velocity U, is by definition the curl of U. So it's a measure of how much the fluid is rotating around each point, right? And in the 2D case, the curl has only one component, which is therefore a scalar. Okay, can be identified with a scalar rather than a vector. And the equation for the vorticity, I mean, this is the reason why we define it, is because the equation for vorticity is very nice. Because if we take the curl of this, then the curl of the gradient goes away. And then the only thing that remains here is the transport equation for the vorticity. So it's simply this equation, transport by the velocity. And on the other hand, the incompressibility, which is divergence 0 for you, tells us the existence of a potential, okay? A potential, so you can be written not as the gradient of the potential, but rather as the gradient perp, okay? Where perp, I will always mean this, okay? This is the, psi is called the string function for you. So it's the potential of velocity, but it's called the string function. Okay, so, and a nice thing that we have is that the vorticity is in reality minus Laplacian of the string function, and this is how an elliptic equation comes in an important way. And I will consider as the solution that I am interested in for the string function simply the inverse Laplacian in entire R2, which I consider it to be the Newtonian potential. So this is the fundamental solution, and now I continue. So the problem, the original problem for the Euler equation is equivalent to this one for the vorticity, okay? And the vorticity is a system in which vorticity is itself the scalar transported by the velocity, which is the gradient perp of the string function, and the string function is the inverse Laplacian of omega. So if you want to think of this problem as simply one equation or one scalar equation, then the coefficient here is therefore a non-local operator in omega, right? So this is the Euler equation is a transport equation but non-local, okay? And the non-locality, just as in the problem Lilian spoke about, okay, it comes as a convolution. Yeah, it's a convolution operator. Laplacian minus 1 of omega. From now on, I understand that it's simply the Newtonian potential, which is given by this formula. And something nice is that the two formulations are actually equivalent in the sense that the velocity can be recovered by simply this formula. The velocity is gradient perp of psi, and therefore can be computed by this explicit convolution. Okay, so this is called the Biot-Savart law, by the way. Yeah? Now, existence and uniqueness for this problem in different classes of solutions. Yeah, say for the vorticity equation, it is enough that we consider initial conditions in L infinity. Solutions remain bounded all the way, and the bounded solution is unique. And in fact, there is no blow up in 2D, and this is already known for many years. Okay, it's not a triviality; it's not a trivial fact that it is completely true. Yeah, well known to be true. Okay, what I am interested in, I am interested in a special class of solutions that are classical, as old as in fact, the origins of these equations. They go back to Kirchhoff or Helmholtz, and say it is natural to consider solutions whose vorticities are very concentrated. So that means solutions so that the velocity field rotates a lot about a certain point, right? Or a finite number of points, just as in this picture, right? So this is a configuration for the atmosphere, right? Say which is supposed to be the fluid, right? Where you have a high vorticity around a finite number of points. Of course, under ideal conditions, you may expect that these points in reality obey some asymptotic law in case that the fluid or the vorticity is very concentrated. So let me consider an ansatz that in reality is consistent with the physics, or actually the mathematical computation you can make with the equation. You can think of vorticity as being literally very concentrated, however, with finite masses around a finite number of points. Finite masses constant in time. This is a characteristic of this problem, that the concentrated masses in reality are not modified in time. Yeah. And so I consider it to be, why not, a Dirac delta. Dirac delta around a certain center, xij of t. So if omega is given by this, of course, psi, which is the inverse Laplacian of omega, is going to be the corresponding linear combination of fundamental solutions. I am, by the way, this is just convenient for me, okay, to make the mass 8 pi rather than 8 pi kappa j rather than kappa j itself. I will tell you more in a moment. So the fundamental solution with this nomenclature is going to be given by this, so the corresponding combination. Okay, analysis of solutions with concentrated vorticities or vortex dynamics, it's also called, right? For the Euler equation in 2D, It's a mathematical subject that has a very long history. As I mentioned, it goes back to at least to Helmholtz, yeah, or even before. In 1858, Kirchhoff, Rose, and other authors actually have considered the problem of formulating the correct dynamics for these vectors, right? Of course, what I am talking about is formal, because it is not so obvious, first of all, even mathematically, it's not so obvious that we can do a nice theory where initial conditions are Dirac deltas, but it's a kind of delicate matter. You can put measures as initial conditions, but solutions that are measure valued are a little bit less obvious. And okay, so let me consider however, just formally, a solution, quotes, of this form. Omega S, the S stands for singular, a solution of this form, where this delta is the Dirac mass. Yeah. So I consider this sum of Dirac masses so that the corresponding side string function is the corresponding combination of fundamental solutions. And then if I compute the operator, I apply the operator to this object, omega S, I get this thing here. And let me observe the following, okay? Gamma is a radially symmetric function, right? So the fundamental solution is radially symmetric in x minus psi I. Dirac delta is also, in the correct sense, radially symmetric. So here I have gradient perp of the radial function times the gradient of the radial function, that's 0, okay? And therefore, that simplifies this, quantity. And what we get is that the operator is given exactly by this linear combination of gradients of Dirac deltas. Yeah. And in order to have a solution, what I would like is that these quantities in the brackets, right, become 0, right? Then in that way, omega S in, at least it's formal, but that's okay. That would make omega S to be a solution. Okay. But when I write down what this means, making the quantity in the brackets 0, then I arrive to this system. This is a system for the points. And what type of system is this? It's nothing but the n-body problem. Okay, if I have n vortices, yeah, this is the n-body problem for a logarithmic potential into D. Yeah. And so this is what it is. And just like we can give you different examples. Of course, the kappa i's don't need to be positive, by the way. It does not matter. I mean, they can be the intensity. They are simply measuring if the vortex is rotating in one direction or the opposite. In fact, if I consider two vortices with opposite sign, I get, for instance, this exact solution. This is just an example, but it's an example called the vortex pair, which is maybe the first non-trivial solution that you can consider of this system. Okay, let me consider now the following question. Well, as I mentioned, this manipulation is formal, okay? And then you can ask, well, I would like to find a solution, which a true solution. Solutions I understand by solution, I understand a smooth function, yeah? So you may wonder if there exists a solution to the true equation, so a solution that is smooth, with as it goes in agreements with the physics it represents, right? However, so that asymptotically, when you move some parameter or you make some concentration parameter go to 0, you would like that solution approaches the singular object, yeah, and the string function corresponding. This is a question. This is a question that you may call the desingularization of vortices. And from the point of view of the theory, it's a very important question because, I mean, if you do a lot of manipulations or with calculus or whatever with vortices, using or dynamical system theory or Hamiltonian systems and so on for the centers, right? Then if you want that represent true solutions of the Euler equations, you have to prove that there exists one, right? And this is the desingularization. This is what we usually do with singular perturbation problems, right? In the elliptic world. So in the distributional sense, this is what I am looking for. I am looking for pairs, omega epsilon, psi epsilon, so that this happens. This question was partly answered by Marchioro and Pulvirenti. Yeah? In 1993, they proved that such solutions exist. These solutions had their supports small and very close to these centers psi j of t. And they managed to prove that if they consider an initial condition, which is strongly concentrated around that point, then those points, then you have this convergent. So for conveniently arranged initial data, you can find this. That's very nice. On the other hand, if you go through their proof gives account correctly of what is happening outside the vortices, but gives little or no information about the behavior of the solution when you are near the interesting parts, okay, which are precisely the point, the vortices. So what motivated us was to use a singular perturbation approach to construct these solutions and finding nice information about the behavior of these near the vortices. Okay, so I am interested then in solutions omega psi, yeah, which are distributionally in some distributional limits. Okay, I achieve omega s and psi s. Now, what are these regularizations? Yeah? I consider regularizations very naive. Okay, because you remember what it was, huh? the psi 0 is this guy. So let me do the following. Let me add here epsilon squared, where epsilon is small number. That's it. That's all. Very simple. Very simple desingularization of the velocity of the string function. Well, I should mention that in reality, with Marchioro and Pulvirenti, you have no information about the velocity field, because the velocity field in reality is in principle for them unbounded. Okay, so the size of it is not well controlled, even distributionally. Okay, now if you do that, yeah, then the vorticity, you desingularize in this way, which is a little bit arbitrary but nice. It's nice in the sense that the corresponding the Laplacian of the psi 0 epsilon is this quantity, which is close to be a Dirac delta, right? So because this is 0, it's a function in the case like 1 over r2 power 4. Yeah, the mass of this is 8 pi. By the way, this is why I use 8 pi. Okay? And then this 1 over epsilon squared times this, all these functions have mass 8 pi. Yeah? Okay, then what would I like? But first, what I observe. Okay, what I observe is that this regularization, of course, satisfies what I want. You know, what I want. In addition, as I mentioned, it satisfies this. This is the velocity field. So the velocity field where this converges distributionally after normalization by log epsilon to a sum of Dirac deltas. Okay, so what is the theorem? That theorem, the result is very simple to take. I start with a solution of the n-body problem, and then the statement is that you can find a solution, a true solution to the Euler system in vorticity form, which is close to this guy, yeah, to the regularizations psi 0 epsilon, omega 0 epsilon. Close in some uniform sense, some stronger topology, yeah, not just distribution or even L1, so it's going to be in a strong topology. And then, just to keep the picture in mind, what we want are solutions omega 0 epsilon that are concentrated around this finite number of points in space. Okay, so here is the statement, and this is joint work with Juan Dávila, Mónica Musso, and Junchen Wei. And our main result here is that there exists a solution, omega epsilon psi epsilon, that is equal to this plus a remainder, yeah, and plus remainders phi and psi and little psi with respect to the basic regularization. And this phi and psi are satisfy this. First of all, the psi itself is very small, okay? The gradient is not bigger than epsilon itself, and psi itself is less than epsilon square even. The phi information I have is a little bit more modest, but not bad, okay? Because you see that what this says is that the remainder is actually a power of epsilon smaller than the main term, yeah? So this phi in relative terms is very small, it's epsilon to power sigma small. You can give, in fact, much stronger information, but I put it in this way just for simplicity. Yeah? So in particular, for the solutions that I found, the vorticity approaches, the corresponding sum of the Dirac deltas. I am missing the pi here, I'm sorry. And then I also have that the velocity behaves in the appropriate way, yeah, but normalized by log epsilon. Yeah? Okay, the proof is, in reality, I don't have time to tell you much about the proof. The proof is technical, but the principle is what we follow in most of these singular perturbation problems. What we need to do is first to guess a good answer for the solution, a good form for the solution, a good approximation, in other words. We need to construct a good approximation. And what is our parameter? Is epsilon. So what we want first is an improvement of the approximation in powers of epsilon. And we managed to do that using elliptic equations and also transport, a combination of the two, which is not surprising because this is the structure of Euclid itself. Then we set up the problem as a coupled system of inner and outer objects. We call them the inner problem and the outer problem, which is a coupled system. And if for the inner problem you satisfy certain solvability conditions, then it turns out that you can solve nicely the inner problem so that the solution of the inner problem arrives small to the remote region. And that makes the inner and the outer problems essentially uncoupled. Okay, this is the principle that we have applied in many problems. Finally, to actually prove the existence of a solution, we use a degree argument. And the reason is that this problem is actually kind of tricky to study with fixed point, with balanced fixed point theorem. However, you have a little bit of compactness, and that's enough to do it using degree. Okay, concerning the improvement of the approximation step. First, let me call gamma 0 to be this guy, log of the U0 guy. Yeah. Well, in fact, the gamma 0 satisfies Liouville's equation, just to keep that in mind. Then what we have is the string function. The basic string function regularized is this guy, if you want to express it in terms of gamma 0. And then what we are looking for is psi in the form of a perturbation of the main object, psi 0 epsilon, and this U0 of y. Y is x minus ij over epsilon. This is what that means. So I want omega to have this form, and the remainder conveniently I write it in the same form. Yeah. And and correspondingly the string function. Okay, if I write down the error that I get, the error of approximation, the operators that I want to make it 0, then I get two terms. Yeah, one that is actually an elliptic operator, right, for the remainder of the string function, and up here what we have is for the remainder we have this equation. So what do we want? What we want is to get a good approximation. Yeah. to get a good approximation in epsilon. And after a little bit of analysis, not much, well, first we realized that psi 0 epsilon can be written in this way, simply gamma 0 times this number, and times this phi of x, this var phi of x. This var phi of x is simply this function, which gives account of the influence of the other vortices in the individual vortex that we are talking about. And the using the equation that I am assuming holds, yeah, psi j dot equals this, then a big part of the error goes away. This is the nice thing. And then I get this equation. So and I have this remainder of order epsilon squared y squared. Therefore, the operator in error actually becomes simply gamma 0 plus this term of order epsilon squared plus the inner string function perturbed. And so this is why it is convenient for us to have the equation. The equation, in one word, eliminates the error of order epsilon. Yeah. Now, if I call f of u to be the exponential and I use the equation, yeah, u0 is f of gamma 0, then the error becomes this thing here. The zero error term, zero, I mean the first error, okay, simply what I obtain by setting phi and psi equal to 0, then the error is this function here. And if you remember that this r is epsilon squared y squared, then this product here is a function of the form epsilon squared times y2 minus 4. So it's a term epsilon squared divided by a power y in space. Y is the space variable, the space transform variable, to power 4. Okay, however, now I realize the following, that I will obtain a reduction of the error if I simply make this operator equal to the first error. Yeah? How do that? Well, it's not completely obvious. Here I have an equation, an operator, which is simply the linearized operator for Liouville equation, yeah? Around this solution gamma 0. But I have this, this multiplication. Well, it turns out that you can solve this problem. You can solve nicely because gradient u0 is connected also with gradient gamma 0, and then you combine the two expressions and you get simply a Liouville type equation that you can actually solve nicely. And that implies that you can improve the approximation by solving these elliptic problems. In fact, you can continue. You can continue by improving in powers of epsilon. But the operator involved here is very tricky because it is identically 0 for all radial functions, you see. So it has a huge kernel. So we cannot really invert with this operator with right-hand sides, which are radial. However, if we combine the use of these elliptic problems with transport equations, these transport equations are tricky because even though you don't lose decay in space, but you lose powers of epsilon, you see, because you have the epsilon square in front of the phi t. So when you integrate, you have to put one of the epsilon square in front. Okay. But if you do things well, you arrive to an error which is of the form epsilon to power 5 times the decay in space rho to minus 3. Rho is the absolute value of y. And then we use an important a priori estimate, which is obtained when you integrate in a large ball. You compute the center of mass of phi and you assume it is 0. And you also assume that the mass, the total mass of the perturbation phi is 0. If in this space, you can actually find, if you have these conditions satisfied, then you can actually find a good L2 estimate for this equation. In fact, what you get is that it's a weighted L2 estimate, which is here. It's an estimate that tells you that you lose 2 epsilons, you lose a log epsilon, but you preserve the same type of decay of the right-hand side. Yeah, this is a power x squared, multiplying the phi. It turns out that this that if you have the error that you had was epsilon to power 5, rho to minus 3, then you get that this guy is like epsilon cubed. And if you compute the new error, then you realize that that allows you to have a contraction principle. Yeah? If you iterate conveniently, use degree and things, then you get the right result. Okay, let me tell you about some variations of it. And so interesting variations, for instance, is the SQG, the surface quasi-geostrophic equation, which is this one. This is the same. It's like Euler, okay, but with a fraction, with inverse Laplacian here, inverse fractional Laplacian, and you get this. If you ask for the same question of the existence of this type of solutions, you can answer it affirmatively. And this is the result with Antonio Fernandez, my postdoc. It's a very interesting result in the sense that this, even though the statement looks the same, but the proof is much harder, yeah, because you need to invert when you make this improvement of approximation and so on. You have to solve these fractional problems, and you also have to, even if S is very close to 1/2 from the above, you have to make the number of iterations to improve the approximation arbitrary. Yeah, so it's a delicate problem. It's not easy, and this is what you get. Okay, let me tell you some words about the three-dimensional problem, the 3D problem. The 3D problem is perhaps the most interesting because you know, the big open problem in this Euler equations setting is the regularity, is the possibility of singularity formation. Understanding regions of highly concentrated vorticity like the ones in these pictures is the correct question. These lines, okay, or regions or tubes with highly concentrated vorticity is what is called vortex filaments. Yeah, and again, the tradition on this is very old. Okay, comes from 1858, the original computations, and then there were very, very beautiful computations by Barrios, who was a student of Levi-Civita in early 20th century, and he found the dynamics law satisfied by this. Let me be more precise. So here I have the same Euler equation as before, and now if you let omega, which is our vector, to be the curve of the velocity field, then you get this equation. You get this, yeah. And what we need to find are solutions with vorticity concentrated on a time evolving curve, yeah. Gamma of t, which is the vortex line, and these tubes, we call them vortex filaments. If we consider a parametrization of this curve, gamma of st, the computation of Barrios, if you assume that this vorticity is like a Dirac delta on the curve multiplied by the tangent vector, which is a natural ansatz again. This is the vortex filament. Then you arrive to this beautiful law. Yeah, this equation gamma satisfies this equation, and this equation is simply curvature multiplied by a number and times the binormal vector. I needed to make, I observed, a change of scaling time here. Yeah, in order that there is a log epsilon in between. And this is the equation for the curve, but in the variable tau, yeah, which is t multiplied by log epsilon. Okay, then let me say, well, here is an explanation of the picture. So this is the vortex tube, the vortex filament, binormal vector, tangent, and normal. And this is the binormal flow. A result of to make rigorous the computation of Barrios is a long-standing problem, and nobody has proved it yet. And I will call that thing, I am not the first calling it that way. We can call it the vortex filament conjecture. It has been stated by several people. So the vortex filament conjecture, I can say, is this thing here, that you can actually find a solution that approaches when you scale time in this form, then you can approach a given solution of the binormal flow. If I use the same statement as before, omega, this W is U0, okay, the same bubble. So as a regularization, then you expect the existence of a solution like this. Nobody knows if this solution exists, even after so many years. On the other hand, in some special situations, it's known. The thin vortex ring, first found by Frankel, and very recently we found it in the case of a helical filament. So you can find it in something like this, traveling with constant speed, or a helix rotating around the symmetry axis. This we proved. In fact, using some observations known in the literature before, we consider the problem for solutions with helical symmetry and also with the traveling waveform. Yeah, this I'm not saying this, but the helical problem can be written in this way for vorticity, and the equation for the coefficient W becomes this if I scale conveniently times, of course, by log x. At the end, what you find is that if you want to find a solution which is in a traveling waveform, then you arrive to this elliptic equation. If you choose F to be you will nonlinearity, it turns out that you can solve this elliptic equation. And this is a result that you can find it in a previa if you would like to see it. So is given in this form. So there exists indeed a solution that works like stated by the vortex filament conjecture. Of course, this problem is simpler than the full conjecture because it is directly a traveling wave problem which reduces an elliptic equation. It's a delicate problem, however, not as delicate as the other. Okay, so my time is almost over. Let me say one thing that if you consider in 3D now, if you consider the no-swirl case axisymmetric, yeah, then and you make this change of variables, you arrive to this equation, which is a scalar, just like in the 2D case. Yeah, so it's simpler because it's a scalar equation. This W is a scalar function. These operators are a little bit more complicated, but they are Laplacian somehow. You have these waves, okay? This is using this and finding traveling waves for this problem is that people formulated the traveling rings or the vortex ring problems, which are elliptic equations. This is an elliptic equation, degenerate but elliptic. And this was first found by Frankel and Berger. There are older things. They were assumed to exist already by these solutions of this type by Helmholtz, and then in our culture, say this is a well-known paper, right? So this is a traveling ring going with velocity constant. Okay, to finish, this is you can also wonder what happens when you put two rings to interact. Yeah, you traveling together with a kind of large speed, but feeling each other. Yeah, and amazingly, Helmholtz already had the intuition of what happened to them. They sort of alternate, reducing their radius or opening or shrinking and going faster or slower, and in kind of in this way, like in this picture. And however, this has not been proven so far. There is a paper by Gerard and Smets, but on another equation, which is simpler, but they took as a model. And recently we managed to prove that there exists a solution like this, in fact, with several rings interacting, and essentially then the result is that if you have radii, this is essentially the radii of the rings, and then they start alternating one across each other. But these are not solutions of elliptic equations. This is a truly a problem in the dynamic setting. Leapfrogging dynamics has been justified by this. The method is what we use for vortices, for point vortices. So thank you very much for your attention.
So thank you very much, Manuel, for the very beautiful talk. So are there questions?
Maybe I have a question.
Okay.
Manuel, thank you. Very nice talk. And I knew the result in 2D. Now, yes. What can you extend to domains if you replace R2, R3 by domains? Is there anything?
Yes.
And you
I stand with with the case of R2 for simplicity, but say in our paper we treat in the 2D case. In the 2D case, the same result is known, except that you have to replace the differential equations by something called the Kirchhoff-Roth system. That in fact you have done beautiful work in it with several.
Yeah, for periodic solutions, I did some work. Yes.
And in 3D, you know, this is very interesting. In fact, the question that is open, that we detected open, and that appeared to interest to a lot of people in this culture, is the steady state problem. So people don't know if there exist steady states. As simple as that. You know, you take a three-dimensional domain, you put no flux boundary conditions, and the question is, well, can we find steady states? And even better if I find them concentrated in a filament. And we have some conjectures in that, but it's not an easy problem because it is an elliptic problem if you want to find the steady states. But it's very degenerate, very, very degenerate. It has lots of resonances and so on. So it's not so simple. With symmetries, it looks like you can do things. In fact, we are doing something with Antonio Fernandez also in this context.
Okay, thank you.
Thank you.
Is there any other question?
Manuel, I'm Silvia. I have a question. In your joint work with Antonio Fernandez, you deal with S between 1/2 and 1.
Yes.
Okay. What happens if S is less than 1/2?
Yeah. This is a good question. Very good question. Now, in reality, in the dynamic setting, S less than 1/2 implies a huge loss of regularity in the solution.
Sure.
So this is the bottom line. That's the main difficulty because we need to solve elliptic equations, iterate. At the end, we have to use characteristics. Yeah,
I know.
If you want to formulate correctly the equation, then you need some regularity. And 1/2 seems to be the limiting scenario in which we can do that. But let me say something that I didn't mention here. There is a recent work by that, in fact, is already published, perhaps. It's in Transactions. It's a paper with Ao Weiwei, with Juan, Monica, and Jun Cheng, that we consider the elliptic equation arising even when S is less than 1/2. Yeah.
Okay.
4-point vortices. And we found, for instance, the equivalent to the vortex pair traveling. Yeah. So but that's an elliptic problem. Yeah. And from the point of view, when you go to that level, to the level of the elliptic problem, in the elliptic problem you don't see big difference between S bigger than 1/2 and S less than 1/2. But in the evolution seems to be more complicated for some reason.
Okay. Thank you very much. And thank you for the very nice talk.
Thank you, Steve.
Okay, is there any other question? If not, let us thank Manuel again for the very beautiful talk. You can use the reaction button at the bottom of your screen to say thanks. Gracias, Manuel.
Gracias. Thank you.
Thank you.
Okay, Filomena, if you want to share your screen now, we can check.
Let us see. Yeah. Okay. Is it okay?
Yes. You can make it larger if you want to.
Yes, sure.
Okay.
Now it's okay, right?
Right. Okay, so I think it's time to go on with our last talk in this session. So it is my great pleasure to introduce the next speaker, Filomena Pacella, from the University of Rome, La Sapienza, and she will be speaking on break of symmetry for an overdetermined problem in a cone. Thank you, Filomena.
Okay, thanks to you, Monica. Thanks to the organizer for creating this nice opportunity to share a bit of mathematics, even in this difficult time. Okay, so my talk is about an overdetermined problem. So let me start introducing the problem. So I have a cone. So what is a cone? I consider a smooth domain on the unit sphere in Rn, Sn minus 1, and I consider the positive cone spanned by this domain on the sphere. So I call it sigma omega. So then I will consider domains omega inside the cone. So typically this domain omega will have two parts of the boundaries of its boundary. One part is the part which is inside the domain, inside the cone, sorry. Usually this is called the relative boundary or sometimes the free boundary. And then there will be another part of the boundary which is on the intersection with the boundary of the cone. Okay, so in particular, we have, sorry, I have a cat behind me. In particular, we would have as domain a spherical sector like this, centered at the vertex of the cone, or more generally, we have domains. So we do not want domains which do not intersect the boundary of the cone, for a reason that will be clear in a moment. So I assume that both the boundary, the relative boundary, and what I call the gamma 1 have a positive n-1 dimensional Hausdorff measure. Okay, so on a domain like this, I will consider a mixed boundary problem, so a simple Poisson equation minus delta u equal 1 in omega. And then on the relative boundary, so the one inside the cone, I impose a Dirichlet, homogeneous Dirichlet boundary condition, while on the other part of the boundary, I will assume a Neumann, homogeneous Neumann boundary condition. Sorry, yeah, this is the, okay. So here, this is the Dirichlet part of the boundary, and the other one is the Neumann part of the boundary. Okay, so to this mixed boundary problem, I add an overdetermined condition, extra condition, but only on the Dirichlet part of the boundary. So I require that the normal derivative to be constant. Okay, so the question that I want to address is whether this problem has a solution. Solution for me means a domain. The question is if there exists a domain omega for which this problem, overdetermined problem, has a solution. Let me tell you that if we just consider the first three equations, so the mixed boundary problem, obviously you have a unique weak solutions if omega is a bounded open domain. But if I add an extra condition, that in principle you may not have a solution. If we take the domain omega that I was showing before, this means the intersection of the ball with the cone, so the spherical sector, centered at the vertex of the cone. And if I consider this a radial function, then it's easy to see just by computation that this is a solution of the overdetermined problem, just because it's a radial function. And so for this domain, we have a solution of the overdetermined problem. Indeed, this function here is just the same solution of the Serre overdetermined problem in the ball, that is the classical Dirichlet overdetermined problem. Okay, so the question is whether this spherical sector is the only domain for which this overdetermined problem has a solution. Okay, as we will see, this depends on the cone. So since the cone is generated by the portion omega on the spherical, on the unit sphere, this will depend on small omega. Okay, so what we could prove with Giulio Tralli a few years ago in a paper which was published in 2020 is that if the cone is convex and U is a classical solution of the overdeterminate problem, classical in the sense that everything which appears in the problem is classical. And then if we add the condition that U is in the intersection of these two Sobolev spaces, then necessarily the domain omega is the intersection of a ball with the cone. A ball which in principle is not centered at the vertex of the cone, but indeed this can happen, that P0 can be different from the vertex of the cone only if the cone has a flat part on its boundary. Okay, so for example, for a strictly convex cone, then the only domain for which there exists a solution is the precise spherical sector. If we have a flat part, then we could have some half a ball like this. Okay, let me just remark that we added this assumption here, which is not really an assumption. In fact, you have to keep in mind that our problem is a mixed boundary problem. And for mixed boundary problem, in general, you may have some problem with the regularity in Sobolev spaces, for example, in the part where the Dirichlet boundary and the Neumann part of the boundary intersect. But when the domain omega is such that its boundary intersects the boundary of the cone orthogonal, it's easy to see that this condition is automatically satisfied. So this is, let's say, a natural condition for this problem. So the proof of this theorem that we got with the Giulio-Tralli is by integral identities, and we were inspired by the proof of Weinberger for the analogous overdeterminate Dirichlet problem. So what I would like now to discuss is, so for convex cones, everything is clear. So if you have a non-convex cone, then you may ask whether you may find another solution. Another solution means another domain for which the overdeterminate problem has a solution. In particular, of course, we are interested in seeing if there is a non-radial domain, something which is not an intersection of the ball with the cone. Okay, so in order to do this, we use a variational formulation of our problem. Indeed, we can see that the domains which are for which this problem has a solution are indeed critical points of a certain functional. Okay, so let me show you what is this variational formulation. Okay, so we have our cone, we take any domain omega inside the cone, and then I consider, as before, the mixed boundary problem. So for the moment, it's without any extra condition. So as I was telling you before, this has a unique weak solution in a suitable Sobolev space, which is the space of the function which are the Sobolev space in function in W12, which are at 0 only on a part of the boundary, actually on the relative boundary. Okay, so I consider this functional which to every domain omega inside the cone associate the energy of this function U of omega, which is the only solution of this problem. Okay, so usually the function of U of omega, a solution of this problem, is usually called the torsion function in the case of the Dirichlet problem. So I will use the same notation for my mixed boundary problem. And this energy is usually called the torsionally energy functional. So keep in mind that the variable for this functional is the domain, is not a function. So this is a functional defined among the domains inside the cone. Okay, so in particular, I am interested in the critical points of this functional. I will tell you in a moment why, and in the minimizers for this torsional energy functional. Okay, let me, maybe some of you know that this functional is quite famous when you put the Dirichlet boundary condition, And the question of finding the optimal domain, so the one which minimizes this torsional energy, is usually called the Saint-Venant problem. Okay, so this is a version of the Saint-Venant problem in the case of mixed boundary condition. Okay, so first of all, what is the relation between this functional and the overdeterminate problem? So the relation is the following. If we consider the critical points of this functional, so critical points in the sense that we differentiate this functional with respect to the domain using the domain derivative technique, which are usually used in a shape optimization theory. So doing this, we can prove that a set omega is a critical point of this torsional energy functional with the fixed volume, if I fix the volume, if and only if the normal derivative of the torsion function is a constant on the Dirichlet boundary. Gamma is the Dirichlet boundary. So what does it mean? That the stationary point, the critical point of this functional are precisely the domain I'm looking for. So the one for which the overdeterminate problem has a solution. Okay, so then in this setting, the results that Giulio Tralli and I obtained claims that in convex cone, the only smooth critical points of this functional are in fact the spherical sector, or possibly the half balls in case that the cone has a flat portion on its boundary. Okay, so these are the critical points. In particular, as I was telling you before, we could look for minimizers. Okay, so if we look for minimizer, then we can see using symmetrization method, we can see that in fact the only minimizers for this torsional energy functional are again the spherical sectors centered at the origin, if the cone has a certain isoperimetric property. So the isoperimetric property, I do not have much time to explain, but the isoperimetric inequality was one of the motivations to study this overdeterminate problem. Anyway, the isoperimetric problem for the cone means that if I consider the minimizer of the relative perimeter fixing the volume, then the only minimizer are the spherical sectors. This was something which was proved for convex cones some years ago by Pierre-Louis Lyons and myself. So anyway, this is just to tell you that in convex cones, which are indeed isoperimetric, or in a bit more general cones which have this isoperimetric property, the only minimizers are again the spherical sectors. Okay, so what we would like to do is now to see what happens, to investigate it, what happens in cones which do not have this property. So in particular, we are interested in non-convex cones to see whether we can have non-radial domains which satisfies the overdeterminate problem. Okay, so let me denote by radially overdeterminate a cone which has this property, that the only minimizer for the torsional energy functional are the spherical sectors. So what I'm trying to see is a condition on the domain, on the unit sphere, which allows me to decide whether a cone has this property, this symmetry property essentially, or not. Okay, so the isoperimetric cones have this property, but we would like to see whether what is the condition to have or not to have this property. Okay, so in order to do this, so we want to use a certain strategy. So essentially, we would like to prove that the spherical sector, which are always critical points, are not minimizers. So if I succeed in doing this, on one side, I prove that they are not the minimizers, okay. On the other side, I have the hope to find minimizers which are not radially symmetric. Okay, so this would be a way to attack the question and to see whether I can have other domains for which the overdetermined problem has a solution. Okay, to do this, we restrict our attention to the class of strictly star-shaped domains inside the con. So what is a strictly star-shaped domains? Strictly star-shaped with respect to the vertex of the con. So we know the definition of star-shaped domain, but it's for our purpose, it's convenient to think, to observe that a star-shaped domain with respect to the vertex of the con is essentially the part of the con which is below the graph of a radial graph of a function. So if I consider a radial graph that I can write in this way, e to the phi z for z times z for z in the domain on the sphere, so this is a function on the sphere. This is the radial graph corresponding to a function on the sphere. And then I consider the domain omega phi can be written in this way of the set of point lambda, z for lambda between 0 and the graph of the, and e to the phi z, which defines the graph of the function. Okay, so to say that the relative boundary is a radial graph, or to say that the domain omega phi is a star-shaped, strictly star-shaped actually, is the same thing. Okay, so this is a particular class of domains inside the con. And now I consider my torsion energy functional restricted to the class of the star-shaped domain. Of course, since the star-shaped domains in the way I denoted it depends on this function phi defined on the sphere, this becomes my functional, which was a functional of domains, in this class of domains becomes a functional, whose variable is a function phi in the class C2. I'm considering C2 functions. Okay, we recall that we have to put a volume constraint. So for radial, if we have a radial graph and I have the domain below the radial graph, then the volume can be written in this way. So then I consider the manifold in the space C2 of the function phi such that the volume is fixed equal to a certain constant C. So what I have to do is to restrict my functional j or omega to this manifold M. And I have to compute the first and the second derivative. Okay, so the first derivative, because of course to find the critical points, but also the second derivative because I'm speaking about minimizers. So my aim is to look at the quadratic form in order to see whether I can find or not minimizer. Okay, I will explain this in a moment. So anyway, if one makes some computation, one can see that the functional restricted to the class, first to the class of star-shaped domain, and then to this manifold where the volume is fixed, has this expression where lambda is a kind of Lagrange multiplier. Okay, if I take the function phi equals 0 in the definition of the radial graph, then obviously the corresponding domain, strictly shaped domain, is precisely the spherical sector. So it corresponds to phi equals 0. Okay, so what I would like to do is to study the stability of the function phi equals 0. Okay, we know that already that this is a critical point of our functional, because we know that it solves the overdetermined problem, and this is equivalent to say that it's a critical point for my functional. I would like to study the stability. Why? Because if I succeed in proving or I giving a condition for which phi equals 0 is not a stable critical point of this functional, then obviously it cannot be a minimizer. And so this means that my con is not radially overdeterminate, but possibly admits other solutions which are not radially symmetric. Okay, so what I want to study is the stability of the function phi equals 0, considered as a critical point of this functional. So I have to write the second derivative, the quadratic form, at 0, corresponding at phi equals 0, on the function v on the manifold M. So one makes some computation and sees that this quadratic form has this expression. Okay, so what we could prove with Alessandro Jacopetti and Tobias Wett, we are writing this paper now, is in preparation, is we were able to give a condition on the domain omega on the sphere, which allows to say that phi equals 0 is not a stable critical point. And this characterization, in my opinion, is nice because it's given in terms of the first non-trivial eigenvalue of the Laplace Beltrami operator on the Neumann non-trivial eigenvalue of the Laplace Beltrami operator on the domain omega on the unit sphere. So what we are able to prove is that if this eigenvalue is smaller than n minus 1, then phi equals 0 is not a stable critical point. So this means that necessarily the minimizer, if it exists, must be another one, so not radially symmetric. So why does this first non-trivial eigenvalue enters into the picture? It enters because I would like to use the corresponding eigenfunction as a test function to test the quadratic form. So in order to do this, considering the expression of the second derivative of my functional, I take the L2 normalized eigenfunction W1, which has a mean value 0, and I extend it by trivial extension to the whole cone. And then, okay, I don't want now to give all details. I make some computation, and one can see that the quadratic form corresponding to the function phi equals 0 computed on W1 on this eigenfunction has this expression, and it becomes negative, which is what we want. We want to find a direction where this quadratic form is negative. Is equivalent to say that this number alpha 1 that I defined before is this number here is less than 1, and to be less than 1, if one looks at the expression of this constant alpha 1, means that lambda 1, the first eigenvalue, is smaller than n minus 1. So this is the way this eigenvalue enters in this proof. Okay, so first of all, then you would like to know whether there are domains on the sphere for which this condition holds. Okay, so first of all, let me tell you that when the omega is a convex domain on the unit sphere, then it's possible to prove that lambda 1 is always bigger than n minus 1, which is exactly what we expect, because we know that for convex cones, we know already that the only minimizers are the spherical sectors. Okay, so but the reverse is not, I mean, so obvious. So we would like to have at least some examples of domains on the sphere for which this condition on the eigenvalue is satisfied, and we could construct some examples. This one, for example, is omega on the unit sphere is a neighbor of the equator, and this other domain omega on the sphere is made by two disks, two geodesic disks, let's say on Sn-1, connected by a small tunnel. So by direct computation, we could prove that lambda 1 is indeed less than n-1. So for the cone generated by these domains on the sphere, then in fact we can claim that the spherical sector is not a minimizer. However, you may ask whether a minimizer exists. So this already tells us that the minimizer is not the spherical sector. So in a sense, you have some break of symmetry. But you may also ask whether the minimizer exists. So if we are able to claim that at least under some condition, the minimizer of this torsional energy functional with restricted to the manifold with a fixed volume has a minimizer, then we provide a real counterexample in a sense. We provide that there exists a domain, there exists a domain, sorry, inside the cone, which is not the spherical sector, which is the minimizer, quindi in particular is a critical point, and so in particular gives a solution of the overdetermined problem. Okay, so the next question we attacked is the existence of a minimizer. So how do we prove that there exists a minimizer? So that's not, I mean, we had to learn several things because this is not an easy question because the cone is unbounded. This is the first difficulty. Okay, so this functional is a functional where the variables is a domain. So these are the typical functional which appears in the shape optimization theory, and for which you want to prove that there exists an optimal shape. Optimal shape means exactly the minimizer. But that is not so easy because our cone is an unbounded set. So we are considering classes of domains inside an unbounded set. Okay. So first of all, let me observe that what is the class of domain in which we would like to find a minimizer. So I'm speaking always, I'm using the word domain. So domain usually means an open connected set. But if I stick with this class, then this is too small to find a minimizer. So I have to enlarge the class of the open sets. And in the shape optimization theory, it's clear, it's well understood that the right class in order to find a minimizer is the class of the quasi-open sets, which are sets which are different from an open set, which differ from an open set by a set with a small capacity. And this is the right class in order to study the level set of a sublet function. This is why this was introduced. Okay, so what I would like to do then is to consider to see if this infimum is achieved. So what is the infimum? Is the infimum of my torsional energy functional, this time considered on the class of all quasi-open set contained in the cone, and which have a volume constraint, which is not exactly equal to C, but less or equal than C, which is more convenient for our purpose. Okay, so my aim is to find a condition on small omega for which this infimum is achieved in this class of a quasi-open set. Okay, so what you do, I mean, we take a minimizing sequence for this infimum, is of course is a sequence of domains omega k, and I would like to see what is its behavior, if it's convergent or not. Convergent in the sense of gamma convergence, but okay, I don't want to make things more complicated now. But anyway, we would like to see whether this has a limit domains, which is indeed a minimizer for our problem. Since the cone is not bounded, it's not obvious that this minimizing sequence is compact. In particular, because the minimizing sequence, omega k, could escape at infinity. So this is the typical situation in unbounded domains. So what we found that it's very useful to use a concentration compactness argument, actually the concentration compactness principle of Per-Lewis-Lyons, which is a concentration compactness principle for function. So we apply this the principle of Lyons to the sequence of the torsion functions. So we pass from the domains omega k to the torsion function that I call u omega k to see whether this is convergent or not. If I manage to prove that this sequence is convergent, then to a certain limit function u star, then the level set where you star is positive will be indeed the limit domain that I'm looking for. Now you may understand here, so then why you want us to take the quasi-open set. Because if I take the level set of a Sobolev function, this in principle is not necessarily open, but is a quasi-open set. Okay, so let me tell you that we used this concentration compactment principle following the approach that had been done for the Dirichlet problem by Bukur in 2000, where he used the same concentration compactness principle in the Dirichlet case. Anyway, since our problem is not a Dirichlet problem, we could not really follow straightforwardly let's say, the strategy of Bukur. In fact, he derived from the Per-Lewis concentration compactness principle. He derived a ad hoc concentration compactness principle for sets that we could not use exactly in the same way. So we had a bit more, I mean, some difficulties more that should have been overcome. Okay, so when we apply a concentration compactness principle, many of you that have applied it plenty of times in semi-linear elliptic variational problems, for example, then you see that you know that there are three possibilities that can occur. So the sequence could vanish, the sequence could have a dichotomy behavior, or the sequence could be compact. Typically, when you study sequences, minimizing sequence using this principle, then in order to get the convergence, one has to study some limit problem. One has to understand what is the limit problem that you have to avoid in order to get compactness. In our case, okay, I do not have time to explain it in details. In our case, the limit problem is the overdeterminate problem in a half ball. Why? Because the cone becomes asymptotically flat at infinity. So if our sequence of a torsion function has its mass which escapes at infinity, then it means that our problem becomes like the domain, like the one in a half ball. Okay, so then we could prove this theorem that if our infimum, the one that I am trying to minimize, is smaller than the infimum that you would get for the half sphere, means for the half plane, so for the half ball in our case, then the infimum is achieved. So this is the typical, let's say, condition that you have. So if you are able to go below the energy of the limit problem, then the infimum is achieved. Okay, so this is what we could prove. But then we would like to have a condition on omega. So when this happens, okay? So a corollary of this theorem is that if we have a domain omega on the sphere such that its Hausdorff n-1 dimensional Hausdorff measure is smaller than the Hausdorff measure of the half sphere, then the infimum is achieved. So in particular, this holds in the two examples that I was showing you before. So in order to prove that this implies the condition of the two infimum to be one below the other one, we used the explicit expression of the torsion function in the half bore or in a spherical sector in order to prove that using this condition, you can indeed go below the, what would be the energy corresponding to the half ball. So then once the minimizer omega star is achieved, then it is a priori a quasi-open set, okay, which in principle can be not connected, can be not bounded, can be not regular, so we don't know anything about this set. But what we could prove is, first of all, that it's bounded. So this minimizes a bounded set. Then that is open. It's indeed an open set. and then that it's connected. To prove that it's an open set is we follow the approach that usually used in shape optimization theory to prove that the quasi-open set, which are a minimizer, are indeed open set. This comes from a regularity property of the torsion function. Then we could prove that it's bounded and connected also using exploiting some properties of our functional. So what about the regularity? So the regularity means the regularity of the free boundary. So the free boundary means the boundary which is inside the comma. And for this, I mean, we are not expert about regularity, but this is there are classical results about the free boundary problem, which go back to Alt and Caffarelli, and recently also to other people like Velichkov and other people. So one can prove that there is a critical dimension, the star, which is not clear yet, is an open question whether it's a 5, 6, or 7, such that the relative boundaries, the free boundary is a smooth manifold, is a C infinity, if we are below this dimension, if the dimension n is below this, the critical dimension, the star, can have countable isolated singularities if n is precisely equal to the star, and has a singular, can have, that's not clear if there exists or not a singular set, but in principle could have a singular set whose dimension anyway is not bigger than n minus the star. And then what is important, on the regular part of gamma star, even if there is a singular set, on the regular part of gamma star, which is anyway is an open part relative to the boundary, the overdeterminate condition holds. And this is what we want at the end. So that's all putting together all these things. So if we have a non-convex cone for which is spanned by a domain on the sphere whose n-1 dimensional measure is smaller than the 1/2 sphere, and such that the first eigenvalue, the first non-trivial eigenvalue of the Laplace-Beltrame operator on this piece omega, on this domain omega, is smaller than n-1, then on one side, we know that the minimizer exists because of this condition. On the other side, we know, because of this other condition, that it's not the radial domain, it's not the spherical sector. So this means that we have found a non-radial domain for which the overdeterminate problem has a solution, which is exactly what we want. So thank you for your attention, and I hope that everything has been clear.
Thank you very much, Filomena, for the very beautiful talk. Are there questions?
Thank you, Ederson.
I have a question, Filomena, very naive. Can you hear me?
Yes, please.
Yes.
Can this eigenvalue be 0?
Can this eigenvalue?
This lambda 1 omega.
Yes.
Yes, no? Because you're in the Neumann.
No, sorry, I do not understand. Can this eigenvalue? I did not understand your question.
Yeah, does it happen that this eigenvalue is 0?
Yeah, this is the first non-trivial. The first one is always 0 because it's a Neumann. It's the Neumann eigenvalue on the sphere.
Okay, so this is the first one non-trivial.
So this is the first one is always 0. And that's not my eigenvalue I'm considering. I'm considering the first non-trivial. So this means the first positive eigenvalue.
Okay. Thank you.
Is there any other question? No questions in YouTube yet. Okay, so let us thank Filomena again. And I want to ask you all to turn on your video, because they are going to take a picture of all the participants, the speakers, and everyone. Okay?
Okay.
So I'm responsible to take the picture. So I just want to ask a few seconds, because there is like a few delay between here and YouTube. So I'm just getting ready. Right. Look at gallery. So I'm just waiting to the YouTube because there is a little delay. For some reason, there is only one screen sharing on YouTube right now, which is Professor Patella.
No, but I should do something. I ended.
Oh, there you go. There you go. No, that's okay now. I think it was just an internet connection thing. So okay, you're good. So I'm gonna take 2 shots, right? Because there's so many people on this meeting. So please get ready. I'm gonna say cheese, but then you have to like stay there for like 5 seconds or so. Okay. So 1, 2, 3, cheese. All right, just one more. All right, just a second. 1, 2, 3. Thank you so much. Thank you so much, everyone.
And now I would like to ask you to turn on your mics. Everybody turn on their microphones. So thank the speakers, our 4 speakers of today, for their very beautiful talk.
Alguém gostaria de já, talvez o que a gente pudesse fazer hoje.
Thanks to you, Monica, and to all the organizers.
Okay, so then have a nice night, afternoon, morning, or
Go to
whatever.
sleep.
Go to sleep.
Bye. Go to sleep.
Ciao.
See you.
Ciao. See you.
Ciao, Monica. Ciao, Liliane. Ciao, tutti. Ciao, Giovanni.
Ciao, Silvia. Ciao, Monica.
Ciao. Ciao Giovanni. Ciao Monica. Ciao a tutti.
Ciao.
Salud, Tomasito.
Yeah, salute, Moniquita.
No wine.
You know, it was too late for coffee for me today, you know?
Yes, I know. I mean,
Because of
you
wine,
are
you know.
German. That's right. I can drink coffee at any time.
Yeah, but it's in the afternoon for you, you know?